So we'll be able to use that to plot and such, right? No, I'm moving on. I think I already did this part. Hey, I'm sorry. I thought those were different tutorial pages. They've got that I have my my part B and C are kind of the same thing, you know?
Oh gosh.
Well, I guess it's just that they have a link to the midway down the tour help HTML. They've got like a sub-HTML link or whatever. I don't know. I'm going on here in part D. I already looked to see. Basic algebra and calculus. This should be more exciting. Huh. I guess we have to use var to define variable. What happens if we just do diff sign u, comma u, without making u a variable? I'm curious. See what happens. What was that code? I lost it. So I'm going to try to just do diff sign u, comma u, without making u a variable. See what happens. Ooh, it didn't like that. See, so before we can do calculus on a variable, we have to say, hey, this is a variable. So that's a little bit different than some other things you've used, right? Maybe. So I have to first declare to Sage that u is going to be a variable by using that u equals var, u in the single quotes. So now I'm putting u equals var. What is that key? I think it's the thing under the quotation mark, right?
Yeah, it is.
Yeah. And now let's see what happens. Hooray! The derivative of sine is cosine. Happy day. With respect to u, right? What should happen if I put a u cubed there? We get 3u squared times cosine u cubed. Hooray! Sage knows the chain rule. What if we do u times that? Look, Sage knows the product rule too. Isn't this exciting? What if we do hyperbolic tangent? Aha. Huh. That's funny. I'm not sure that it's doing that right. The derivative of hyperbolic tangent is hyperbolic secant squared, for what it's worth. That is hyperbolic secant squared. So here's the thing. Cosh squared minus sinh squared is equal to 1. So hyperbolic sine and hyperbolic cosine are kind of a little bit quirky in the sense that they satisfy, instead of cosine squared plus sine squared being 1, it's cosh squared minus sinh squared being 1. So if you divide that by sinh squared, you get 1 minus tang squared equals to hyperbolic secant squared. So with that in mind, the answer that was just given was 1 minus tangent squared of u. That is the hyperbolic. This is hyperbolic secant squared. It's just, you know. There might be a way to simplify with Sage. I don't know what that is right offhand. Okay. What's next up? So we can take derivatives. Can we solve equations? It says let x be the variable x, and then you can solve that quadratic. Let's try it out. Solve. So apparently either x is equal to -2 or x is equal to -1. Since we can factor, I think we agree, right? I wonder if it does complex. What happens if we change that 3 to a 4 and the 2 to a 5? Take that, Sage. Oh, Sage is like, no problem. The solution is -2 minus I or -2 plus I. So check it out, it'll do complex without any kind of extra prodding. It's already set up to do complex. It's just, it uses capital I for the notation for, like, you know, square root of -1. See that? Pretty neat. Ooh. Interesting. Oh, that's very, look at that. This next example is really cool. Does it automatically set it? I guess it sets it equal to 0, doesn't it? The solver. That's funny. Oh no, so I guess the default, so this is interesting. If you don't notice that we didn't actually say solve an equation in the first thing, we said solve a polynomial. It just automatically defaults that to be equals 0. It's kind of funny. So if we want to, but we could put equals 0 to be less, you know. And I guess we're solving with respect to x. Why did it do what it did? So you guys tell me, look up here for a second. I just went through the tutorial solving the quadratic equation. ax squared plus bx plus c equals 0 for x. I've made x, b, and c variables. I didn't declare that a was a variable, did I? So what has it made a equal to?
Probably whatever you had in the very beginning.
That's right. What do we make a at the start?
5.
5. So like x is minus b over 2a. 2a is 10. That's why there's tenths here. So to get rid of that, I could just, like so. And that's something to keep in mind is, like, once you declare a variable, it's just going to remember it until you clear it. There's got to be a way to clear variables. That's probably one of the first things we should learn is, like, how to clear all of the variables as you're working. But I am just going to forge ahead for the moment. Oh, look, it'll solve systems of linear equations. See that? We can let x and y be variables. We can solve, you could just make a list with brackets like that to solve more than one at once. That's neat. Cool. So if I was to do 3 variables, I wonder what it would do if I gave it a system with infinitely many solutions. You need to put, can you put 2x, or do you have to put like 2 times x? Well, apparently you need to you have to put the stars, for the star for multiplication, it is required. Wow. That's nice. So check this out. I gave it 3 variables, x, y, z, and I asked it to solve x plus y plus z equals 0. You know, 2x plus 2y plus 2z equals 0, and x minus y equal to 0. So 2 of those equations are the same equation. So like I knew if I have 3 equations and 3 unknowns and I only have 2 actually distinct equations, the solution set should be like a whole line, because basically you're looking at 2 planes intersecting in 3-dimensional space, and the solution set will be a line through the origin. And it gives you back a parameterized set. Minus 1/2 R1, minus 1/2 R2, and then z is equal to R1, so it's an infinite solution set where the parameters are 1. Nice. If I change even one of those numbers on the middle equation, it'll just give us a single solution. Like make that 2 a 3. See, 0 is the only solution. What's it? So this one gets a name, huh? Jason Grout. Oh my goodness, what on earth is this thing? Ah, so you can define equations separately and then list them if you want to kind of like divide and conquer. See that?
Mm-hmm.
That's nice. And there's also a numerical solver. Let's see here. What does the 30 mean? The argument is the number of bits of precision. Oh, so 30 bits. I see. So we can solve sine equal to cosine over a certain range. I'm moving on to solving equations numerically.
Okay, I was like, with the camera, I was just like, where are you?
Oh, I'm sorry. I just skipped down a bit. I mean, the nonlinear system is interesting, and the numerical approximation is great.
No, let's move forward. Let's
But we can. I want to get the plot here before it gets too much later. How does this work here? Theta equals to variable theta. All right, I think I get that. And then, what's that next line mean? Solve cosine theta equal to sine theta theta? What's that? It looks like it didn't do anything. lost Alex.
No, he's still here.
He's still here.
He left his backpack.
He left his backpack.
And his wallet.
And his wallet.
Yeah.
Like, even if he didn't care about his backpack,
He
his
left.
wallet is still here.
He left his wallet. Now that sounds fun. Sorry, I behave. Oh, hi.
See?
We weren't talking about doing anything with your stuff or anything.
That's the sign that I was coming back.
So, yeah, apparently the solution to sine theta equal to cosine theta is given by sine theta equals to cosine theta.
Mm-hmm.
So, okay. That's, Okay, so the solve doesn't really know anything to do with that. That's funny. Oh, okay. But you could look, you could use find root on that. Let's see here, let's try that. So if we do I'm going to do theta instead of phi. I don't know why I changed to theta to phi or phi. Of course. So that's pi over 4. That's where sine theta is equal to cosine theta. Yeah. Okay. So back to differentiation again, apparently. Oh, that's interesting. Fourth derivative of sine of x squared. So you do... Cool. Try that out. I'm going to do theta, though. There you go, that's the fourth derivative of sine of theta squared. But why do 4 when you could do 44, you know? Oh, that's why. Nobody wants to look at that.
No.
How about, can I break it? What if I did 444? Huh. Oh. Oh. It's like, no. Oh, well. So you guys, in Calculus 3, remember the torsion for a curve? No? Curvature?
At this point, I'm having trouble remembering things earlier today.
Earlier today is trouble. I know my brother had something similar to Sage is called, there's two commercial products that are like Sage. The one is Mathematica, the other one's Maple. These are the dominant products. There's also something called MATLAB, which is commonly used in industry. Like when I was working for the government, pretty much everything the Navy does is in MATLAB, a lot of it. And then if MATLAB's too slow, then they'll use C++ or whatever. But anyway, in Maple, my brother had this a curve that printed out the formula for the torsion. And if I remember right, I think the formula for the torsion was something like 50 pages. So like, the things you can do with a computer now are just sometimes just totally ridiculous. Like, who's ever going to actually do anything with that formula? I don't know, but one of the research projects I worked with on a student, we were looking at this differential equation that, like, the differential equation itself would be, hundreds of terms. Trying to solve that. Like, it's a pain to even write with anything except for a computer. Ooh, partial derivatives. So, something else from Calculus 3? Oh, look at that. So is that function? Is that how to define f of function there? I wonder what syntactically the difference is between. See, this is a rather different way to make f a function. Like it's not f of. See that? So if I went to the next step and said something like f of 1, 2, it probably would just tell me to go fly a kite or whatever, right? No, you can't do that. That doesn't make. Well, it did tell me 69. Heh. What's 1 plus 4 times 17 is what? 68, isn't it?
Yeah.
68 plus 1 is 69. Oh, but then it's giving me a warning. Substitution using function call syntax and unnamed arguments is deprecated and will be removed. In other words, enjoy this while it lasts because it's going away. So, yeah, that. Well, all right. I don't know what to make of that. So the notation is f dot diff x, huh? Don't want to be YouTube famous, huh?
Yep.
Yeah. It's kind of like, I want tens of views to this video soon. I mean, it's very, very exciting stuff. So 2x, huh? If we differentiate with respect to y, we ought to get what? 34y? Yeah. Huh. So I guess you could also do like def, what was it, def, was that it? Or was it def and, forgotten now. We did function earlier, right? How do we do it? DEF or DEF? Yeah, DEF. So if I do DEF, we call it F2. Let's see if I can make a function of x and y. So I already have x and y made variables, so just say g x comma y, return x squared plus 18 times exponential of y. See if that works. All right, well, didn't break it yet. And then if I do g of 1 comma 0, I ought to get 19. Okay. So you can properly define functions of two variables using the def that we did before. Or you can work with this, like write it as f equals to something, and then you've got to do this dot notation, like f. I wonder if I can do that for here. What if I do like g? See, I'm wondering, this probably won't work. This probably won't work, dot diff. That shouldn't work. Yeah. So I guess if we want to use the partial differentiation, we have to define functions like I did on line 75 up here. Oh, well. So, oh, my eyes. Sorry, here. we can do integrals too. And the code for integral is shockingly integral. Partial fractions decomposition, that's kind of cool. So the integral of x sine of, what happens if you ask it to integrate something that can't be integrated in closed form though? What if we take away the x? What's going to happen? Oh! Whoa! That's right, sine of x squared can be integrated if you know about the ERF. The ERF. Look at this. This is the integral that involves imaginary jibber jabber for sine of x squared. Do you remember this from calculus 2? I certainly hope not, because if like Rakovich is teaching that in calculus 2, that ain't right. On the other hand, if I put an x before it, then that's, come on, that's, you know, that's like taking candy from a baby. Which is incidentally a very bad saying, if you really think about it for a second. Doesn't make sense, honestly. So apparently we can solve, oh, hey, want to try to solve that differential equation? So here's how we can solve differential equations with Sage. We, oh. Huh. So this is how we declare a variable and then a dependent variable. Interesting. So did you notice, by the way, that if you want to put comments in your Sage code, you just do like hashtag whatever. I'm sorry, excuse me for that. Pound whatever. My apologies for bringing unnecessary hashtag to this class. Hashtag, we don't hashtag. Wait a minute. It seems wrong what I just said. Hashtag, no hashtags? Run this thing. Wow. So t is the independent variable, x is a function of t. We're looking at the differential equation, which is differentiate x with respect to t plus x minus 1. And there's the solution. Huh. So if we wanted to solve, if we wanted to look at like the second order, like part A earlier, I think that the notation for that would be like diff. Maybe? There's probably a better way to do this, but diff xt plus x equal to 0. Maybe. Ah. I guessed right. So, like this code, this would be the derivative of the derivative plus x equal to 0. So this is like x prime prime plus x equal to 0. Solve this differential equation. X is the dependent variable, t is the independent variable. Solution, some constant times cosine plus some other constant times sine, which is what I mentioned earlier and we found with Wolfram alpha. So the thing here that makes this inherently better than Wolfram alpha is you could build the code that we're looking at into part of a larger program of analysis. Like it's not just something to take a screenshot of, you know, kind of disposable fact. This is a thing that you can link together and make part of a larger program, mathematical program if you want to. But anyway, Laplace transforms. We'll skip that. Let's see here. But Laplace transform is something you study in differential equation. I'm guessing next he's going to show us how we can solve systems of differential equations. Fancy. It's hard to read, but it says that. It's funny. Okay, well, anyway. I don't think we need to learn how to take Laplace transforms in here. And I think Euler's method for systems of differential equations is essentially irrelevant to us in here. Let's get past that. Special functions, bless their heart, but we'll move on.
That's the end.
Yeah. Well, no, that's not the end, but it's the end of that part. Yeah. Ah, plotting. This is the end right here. Let's see here. So you can do things like make circles. Ah, cool. So you guys know about RGB colors? Red, green, blue. It's like a triple, and you choose different triples for different, you know. Like I think it's the red, the green, the blue. So I think if you do 1, 0, 0, it should be red. And if I'm right, if I do 0, 1, 0, that should be totally green. If I do 0, 0, 1, it should be blue. And then if you take, you know, various sort of combinations of those, you get other colors, right? Like what's 1, 1, 1? Oh no, it's gone. So white is all the colors, right? So if you do red, green, and blue equal weights, then it's just white. So 1, 1, 1 is white, although I don't advise graphing in white on a background of white, especially in 2021. Just saying. Let's see here, 0. Elizabeth's like, no, no,
Sorry,
I'm not going to be part of this.
Sorry, just end of the day, just kind of hitting me.
Anyway, so of course you can find a website with like I'm sure there's like a resource. If we were to Google RGB chart or something, we could find, you know, a nice RGB color picker. Check it out. I don't know. So if I want like magenta, I do 150, 56, 150 apparently. So well, that didn't work.
Looks black.
It's like, that didn't quite translate, did it?
Well, if you took it back to the corner, what would it do?
Something got lost in translation there, huh? Oh well, I tried. So you can maybe if we could put a slider in there and slide the color around, we could find it or something. I don't know. Actually, I don't know how to. By the way, it's something that would be interesting to know how to implement. Is a slider in Sage. I don't know how to do that. I never figured out how to do that in MATLAB either last year when I was working for the Navy. It's something I always wanted to do. Like being able to put a slider into MATLAB would have been huge for what I was doing. I could never figure it out conveniently. And other people would tell me, oh yeah, it could be done, blah, 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 but not the same as doing it. Anyway, oh, a filled circle. Ooh. Syntax error. What did it not like? I did something wrong here. What was the syntax error? Maybe it didn't like my RGB. Oh, wait a minute. Maybe you have to have a number between. Sometimes the RGB has to be between 0 and 1. It may just not like that I'm putting something between larger than 1 there. I wonder. Yeah. What? Where is this error coming from? Lines 2-2. Well. Man, are you guys getting this error too?
Nope.
Oh well. Anyway, it's not happening to you, so great. Let's see here, I'll go to the next one. Well, I've got, it's giving me an error, but if it's not giving you guys an error, whatever. Anyway. Let's see here. I'm really more interested in how to plot basic functions, like here, plot cosine from -5 to 5. That's interesting. Haha, there you go. That's not bad at all, is that? Look at that cosine. The cosine plot's pretty nice. Yeah. Not bad at all. I think we could plot tanh too in the same way. If I just like, I told you guys that we'd take a look at tanh. Here it is. So tanh kind of levels out to ±1. And that's easy to understand because if you look at the formula for it, it's e to the x minus e to the minus x over e to the x plus e to the minus x. And if you think about this formula, right? If you think about that formula, as x goes to infinity, e to the minus x goes to 0. So you get e to the x over e to the x, which is 1. And if x goes to minus infinity, well then e to the x's are trivial. And e to the minus x's are totally dominating the formula, and you get minus e to the minus x over e to the minus x, which is e to the minus 1. And that's why you get -1 going to the left and 1 going to the right, like that. Makes total sense. So let's see here. You can make x a variable. What's this parametric plot thing here? Try this on here. Ooh. So you could have made the variable like t if you wanted to. I like to use t for parameter, you know, personally. Then this would feel more right to me. At least I don't like to use x for a parameter. Just seems off to me. So that's pretty cool. So we can plot parametric curves like that. Huh. I hope they show us how to adjust the plot window here pretty soon. That's going to matter to us. Whatever we do with Sage, we're going to want to adjust plot windows, right? So we should be looking for that as we're looking through this here. Oh, that's cool. So here they're showing us how we can plot 3 parametric curves at once. That's nice. Ah, cool. Let's see here. What's this next thing? I don't quite understand what I'm talking about in this next one here. Oops. Yeah, be careful when you cut and paste. If you leave the Sage in, it doesn't like it. Oh. Any of you guys successful in cutting and pasting the part here? It's like a good way to produce filled-in shapes, blah, blah, blah. Did you guys get this one to work?
Give me a second.
Oh. I think I know what I did wrong. I had an extra colon that didn't, it was part of the commenting, it wasn't part of the code. Whoa. How's that work? So there's a polygon command that apparently makes a polygon based on a list of vertices. So like that first line here is giving us like a list of vertices. And the thing is that there's so many of them. There's 200 of them, right? So I don't think we can even see them. They're like so, like you can't even see that there's, you know? I think if I'm right, if I change that 200 to like 20, maybe we could see it. Maybe if I made it like 4. Jeez. Well, it's not working out well for me today, is it? I tried. Let's see here. Well, if I understand the syntax correctly, let me try something. Oh, wait a minute. I'm doing this all wrong. How can we find out the code for polygon? You guys tell me. Do we want to change this a little bit? Suppose we want to make a polygon like they're doing. What should we do? We should do polygon question mark, right? And that should show us what the deal is with polygon. Right? And it'll give us a more simple example to try, like this one. That should be a triangle. Right? There you go. And then if we do, like back up in here, if I make L equal to, you know, oh, sorry. I'm trying to make that example less weird. If I make L, so okay, so we can make L a list of points, which we just do. To make a list of points, you just do like words. So here, I changed that example so it's less bizarre. See, guys? So I make L the list of points, like 0, 0, 1, 1, 0, 1, like that, and then it polygon L, RGB color, whatever. So I could imagine us using this command possibly. I mean, I don't know. If you want to make a square, we could add what? 1, 0? Oops. Comma. Oops. Oh, look at that. See this, guys? That is not a square.
No, it is not.
So the order of the points matters to polygon. Apparently. I should do like, if I can imagine myself going around the square, start at the origin, go to 0, 1, go up to 1, 1, come back to 1, 0. Yeah. There we go. Now we got a square. So the order of the points in polygon matters. You gotta list them as they're traversing the edge of the polygon, otherwise, yeah, cool. Ooh, here's how we can put text inside a plot. There's this, you see that show command? We're gonna need to understand that. Show. So piece polygon. So I let t equal that, and then I show p plus t. Look at that. That's funny. See this? So, I mean, the hypotrochoid is the label for the funny-looking, curvy-looking, triangle-y thing that was in the tutorial, right? Which I changed to a square. But I think it's funny, like it's stuck the label way over here because it's anchored at 5, 4, right? If I want to put it down here, I think I could just change the 5, 4 to a 1, 1. And then that would look better, right? Well, sort of better. Now it's kind of overlapping, see that? Calculus teachers draw the following plot frequently on the board, not just one branch of arcsine, but rather several of them. What is that? Okay. Oh. I think he's plotting sine vertically. What's going on here? Yep. So, what's float? Do you guys know what float is? What's this float pi? Do you guys have computer class or no? You had like programming, like introduction to programming or anything?
No, the only computer
No.
class I took was, here's how to use Microsoft Word,
Oh,
PowerPoint,
okay.
and Excel.
So float here probably refers to like a floating point number. It's a data type. I suspect if I just got rid of float and just did like 2 pi, it would still work. You can try. See what happens. It may be that this srange command, though, requires floating point numbers. And that's why that's there, because otherwise it gets an error. No. I'm not sure why they had float there. What's line? Wait, why is it? I don't understand what this thing is doing, honestly. Well, whatever. I'm going to look at this contour plot next. He says f is equal to lambda. And then what? Let's see here. Whoa. That's interesting. What is the role of lambda here? Is that part of the contour plot command or something? Huh. I mean, I think we're looking at the contour plot of cosine x times y on the -4 to 4, view window, right? What's this lambda here? I'm going to look at the documentation for contour plot and see if I can find out more. So contour underscore plot, question mark. Let's see what it tells me. Curious. Well, when I look at the examples in contour plot, I don't see anything quite like the code we just copied from the tutorial. Hmm. Well, maybe lambda's an option. Let's see what happens when I get rid of lambda. Ah. Oh, that lambda has to be there. Oh, okay, so that code, that lambda code, is just a sneaky way of making x and y variables in one line. Like, here's what I did. I changed x, y are variables, and then f is equal to cosine x times y. And then I did the plot and it did the same thing again. So like that line I had there originally from the tutorial, like lambda, x, y, that's a way of saying like f has variables x, y, and the formula is this. So I'm not sure. Okay. That's the thing about these kind of like programs. There's like always some kind of sneaky faster code or something. Ooh, three-dimensional plots. I'm excited about this. By the way, guys, once we're done with this, we're out of here.
What, just one?
This page. Because the rest of the time this week I will, no, you can use it to the, where's your product?
Bless you.
Thank you. My apologies. Yeah, look at that. Paraboloid. Fancy pants. Let's see here, what else can we do? Did you see it? We can also do parametric plots. Let's see here. I see. I wish we could make it more like a wireframe or something. Like I mean, I kind of have the same criticism of these 3D shapes as I do of like the ones that were created by GeoGebra. They don't look very good to me. Like I really like to see a grid, like a wireframe grid on the surface, and